In this lecture, we strive to streamline a few of the formulas for the application of the Rayleigh Ritz method with 10 functions. We are making this lecture in preparation for another video that we are making and where we write a Mathematica code for the Rayleigh Ritz method. The boundary value problem that we will tackle in this lecture is of the form minus d by dx of the product of p of x and dy by dx plus q of x times y equals f of x, where p is continuously differentiable and positive on the interval from x equals a to x equals b, q is non-negative and continuous, and f is continuous. Y of a and y of b are both 0. We will use 10 functions for our basis functions for the Rayleigh Ritz method in this lecture. We subdivide the interval ab using the nodes x sub I, where I goes from 0 to n plus 1, with x sub 0 equal to a and x sub n plus 1 equal to b. This results in n plus 1 subintervals where we set the length of the ith subinterval equal to h sub I minus 1, which is equal to x sub I minus x sub I minus 1. The ith 10th function, which we call phi sub I, equals 0 when x is between a and x sub I minus 1 inclusive. Phi sub I of x is x minus x sub I minus 1 over h sub I minus 1 when x is greater than x sub I minus 1 and x is less than or equal to x sub I. Phi sub I of x is equal to x sub I plus 1 minus x over h sub I when x is greater than x sub I and x is less than or equal to x sub I plus 1. Phi sub I of x is 0 for the rest of the interval. And so phi sub I prime of x is given by these formulas. If phi of x is the approximate solution to the boundary value problem, then phi of x is given by this sum, where each c sub j is a real number for j equal to 1 to n. We can solve for the c sub j's from a system of equations that we write as a matrix system. Let the coefficient matrix of this matrix system be the n by n matrix R, whose entries we designate as lowercase r sub ij. The entry r sub ij is given by this integral formula. We had shown how one can derive this well-known formula in another video whose title is Introducing the Rayleigh Ritz Method with 10 Functions. We are including a link to that video in the description of this video lecture. If uppercase C is the vector of the c sub j's, then the matrix equation is given by the matrix R times the vector C equals some vector S, whose components we call S sub I, where I goes from 1 to n. We also provided a derivation for the formula for S sub I in the lecture introducing the Rayleigh Ritz method with 10 functions. For I equals 1 to n, S sub I equals this integral. The matrix R is tridiagonal with only the entries R sub I, R sub I minus 1, and R sub I plus 1 being possibly non-zero. The matrix R is also symmetric. The entry R sub I is given by this formula. R sub I minus 1 is given by this formula. And R sub I plus 1 is given by this formula. The component S sub I of the vector S is given by the sum of these two integrals. Observe that this integral for R sub I is used again for R sub I minus 1, and it is not the only integral used more than once. So as not to have to recalculate each integral each time we have to use its value, we pre-calculate each integral and store the value in some indexed variable. Then we only need to call the variable where the value of a particular integral is stored the moment we have to use the value of the integral. We set the first integral in the formula for R sub I equal to a sub 1I. We simply increase the index for the next integral, so that the next integral is a sub 1I plus 1. The range of I for a sub 1I is from 1 to n plus 1. We set the third integral equal to a sub 2I. And we set the fourth integral equal to, this time, a sub 3I. For both a sub 2I and a sub 3I, I goes from 1 to n. In R sub I minus 1, the first integral term is minus a sub 1I. we set the next integral equal to a sub 4I. The column number I minus 1 should start at 1, and so I should start at 2 for a sub 4I. I ends at n. In r sub I plus 1, the first integral term is minus a sub 1 I plus 1. For the second integral, we merely increase the index in a sub 4I by 1 to get a sub 4I plus 1. In s sub I, we set the first integral equal to a sub 5I. And we set the second integral equal to a sub 6I. And so we have r sub I equals a sub 1I plus a sub 1I plus 1 plus a sub 2I plus a sub 3I, with I going from 1 to n. R sub I minus 1 is equal to minus a sub 1I plus a sub 4I. I goes from 2 to n. R sub I plus 1 is minus a sub 1I plus 1 plus a sub 4I plus 1. I starts at 1, and since the column number I plus 1 can go only up to n columns, the maximum value of I for R sub I plus 1 is n minus 1. S sub I is a sub 5I plus a sub 6I with I going from 1 to n.